Hiya, in this video, we're going to have a look at integrals with respect to trigonometric functions. Let's just do a quick reminder of what the derivative of sine and cosine are. So if we start off with f of x equals sine of x, that's just a reminder that the derivative of that is cosine of x, so f dash of x equals cosine of x. If f of x equals cosine of x, then the derivative is equal to negative sine of x. So you might be able to see that if we're working backwards here, there's definitely a relationship that we can exploit here. So let me show you what the formula sheet looks like. This is just a one-sheet formula sheet. So you get a formula booklet actually within the IB exam itself, but you can see here that here are the standard integrals that you're given, including the integral of sine of x and the integral of cosine of x. Note that there's no integral of tan of x that you are required to recall, although, as you'll see later, working out the integral of tan of x can be done as long as there are certain boundary conditions that are considered. If you think of all those asymptotes, that might give you a sense of what we'd need to consider. Just like for the integral of 1 on x, we need to clarify that x is greater than 0, and in order for that to work. Okay, so that's the formula. Since this is the formula sheet, then you can see that sine and cosine is required, but nothing else. And you'll see here that the integral of cosine of x is given by sine of x plus c. So when you're going backwards, the signs are also kind of gone backwards. So from the integral of positive cosine, you get positive sine, but the integral of sine equals negative cosine. And I'll go back to the whiteboard in a second and show you why. Actually, I'll do that now. How about I do that now? So, I mean, if you think of it backwards, if I've got the integral, if I've got the integral of positive sine of x with respect to x, then that's going to be, well, the integral, the antiderivative of sine will go to cosine, but it's the antiderivative of negative sine. So in order to compensate for the fact that I've ended up with a positive sign, it's kind of like, well, I must have started with a negative cosine, because if this was f of x equals negative cosine of x, then the derivative would be negative sine of x, which would be positive sine of x, and there's the positive sine of x there. So that's why there's a bit of a flip there. So that's negative cosine of x, and in a similar fashion, the antiderivative, the integral of cosine with respect to x, well, moving our way backwards here, we've perfectly got cosine of x here. So the antiderivative, the integral, is going to be just simply sine of x, and of course we add the c in both sides. And as usual, my video has covered it, but there you go, there it is there. Okay, so that's the actual formulas themselves. And what I thought I might do is just go through some examples from the textbook. So looking at the textbook here, it's back to chapter 14 for the integral of sine and cosine. It starts off by going through the general rules. So you can have a look at that at some point if you need to. But importantly, we're going to go down to exercise 14E, and I'm just going to go through question 9, question 10, and question 12. So that's where they're coming from. So back to the whiteboard. Zoop, zoop. There it is there. Question 9. It's the integral of cosine x sine squared x dx. And we're going to use the substitution method to solve this. We just need to remember those extra special rules for trigonometry to make it work. It's not too bad though, it really isn't. First thing I'll do, just to spell it out a bit, is I'll just remind you that sine squared x is the notation that means sine of x all squared dot dx. And I hope by doing it like that, you might see that there is definitely an inside function, sine of x, which has then been squared. So inside function squared, and then we've got a cosine function here. Now, if you're thinking ahead, you might remember that the derivative of sine is cosine. And so we've got a match here. Remember, the derivative of the inside needs to be part of the product in order to move ahead with the substitution rule. So let's go with the substitution rule. I'll switch it over to the side for a second. So we've got let u equal sine of x, the inside function. Then du is equal to the derivative of sine, which is cosine, x with respect to x. So we can see here that we've got a straight substitution here, and we can see that that part and that part is there and there. So we are good to go for a substitution. So that's equal to the integral of, so the cosine x dx becomes du, and the sine x becomes u. So we end up with u squared du. Remember, that's the name of the game, to change the integral so that it is so it just has u as the variable with respect to u. So that's the du bit. Okay, so now we can integrate that. That's a fairly straightforward one. It's just the power rule. So I bump up the power by 1. So it goes to u to the power of 3. And then the reciprocal on the outside. So 1/3 u to the power of 3. And of course, the plus c that we are required to do for an indefinite integral. And then it's a substitution back. So it would be u cubed. So u is sine x. So I'm going to put the sine x in. And I'm going to go back to my proper notation for powers of trig, and that means u cubed becomes sine cubed x. So remember, that means sine of x and then cube the result plus the constant value c, and that's it. Now the textbook might have, sorry, and I forgot the third. The textbook might have sine cubed x all over 3 plus c. That's fine as well. 1/3 or something is the same as dividing by 3. So either way is perfectly fine. So that's question 9. Let's flick on to question 10, I think. Yep. Like so. So we've got the integral of sine of x over cos of x with respect to x. So I don't know whether you can see that or not, but just a reminder that that tan is equal to sine on cos. Okay, so we've kind of working out the integral of tan of x from first principles in a sense, in a way, not first principles, but by calculation rather than by formula. But this only works if cosine of x is greater than 0. Okay, so just be mindful of that, there are specific conditions required in order for this integral to work. Alrighty, so keeping that in mind, just briefly, cosine x can't equal 0, because if it did, then you'd be dividing by 0. And cosine of x can't be less than 0, because then the integral substitution we're about to do won't work. We'd have to do a different one for cosine of x less than 0. So keeping that in mind, we do the usual. Let u equal, so again, just trying to keep track of what the function is here. This is sine of x multiplied by 1 on cos x. Okay, we can split this. We can always split a fraction up. So a over b can always be split up to a over 1 times 1 over b. And we don't really need that a over 1. So it can always be split up. So effectively, we've got something multiplied by 1 over something. So in this case, we've got sine multiplied by 1 over cos x. And that's where our inside function comes from, because we've got 1 divided by as the outside function and cosine of x being the inside function. And so we let u be the inside function, cosine of x. So therefore, du is equal to negative sine of x. Okay, that's really important to remember what we're doing there with respect to x. So it's du equals negative sine of x dx. Now you can go straight for a substitution there if you keep your wits about you, but if it helps, you can multiply both sides by -1, and you can get negative du is equal to sine of x dx. And the strength of doing that, if you want to, is that this now perfectly replicates this bit I'm just highlighting here, sine of x dot dx. So that bit has been highlighted. Just get rid of this bit. So that is now equal to the integral of 1 on u du. Again, I'll just point out that the sine x dx has been replaced by negative du, so that'll be negative 1 on u du. So we've got negative du, and that's where the negative 1 comes from, and the cos x is now u. So now we can work out the, sorry, I just turned my iPad off. Now we can work out what the integral of that is. The 1 on u becomes ln u, and then we've got the plus c, and the negative just goes out the front there like that, no dramas at all. Okay, the reason why the negative doesn't have any impact is because effectively that negative 1 up out here can be taken outside the integral sign. Okay, using standard integral rules that a constant a constant part of it can be taken outside. Okay, so it's just a negative ln u plus c, which is then equal to, it's going to look a bit weird, but it's okay. Ln, now u is cos of x, so it's ln cos of x plus c, and then we're done. Okay, next one's a bit trickier. So there's those two examples, so you can see them side by side along with the rules, and then I'll flip over to the next page because it's got a few more lines in it. I wanted to have it all on the one page. Okay, so I'll keep it zoomed out. I'll write fairly big. So question 12 is in a couple of parts. I'll just flick over and show you. It says let f of x equal to the natural log of cos x. The natural log of cos x, which means that cos x has to be positive, right? Because if cos x was negative, then the natural log wouldn't exist. So we're going to first of all show that the derivative is equal to negative tan x, and the second part is hence show that this funny old expression here, I'll find it. And I wanted to say a little bit about language here. In fact, look at question 11 as well. You can see find, that means you should show some calculations. You can see write down, which means that just an answer is sufficient for full marks. Here you can see show, so you should do calculations. This is a really important word, hence. Hence find this means that you must use the result from part A in order to solve part B. You can't go off on a crazy tangent. It should be utilizing the result you found. And we can see there's a tan x and a tan x here, so there is definitely a relationship. Okay, so that's really important for you to understand the language there in order to maximize your marks. Okay, back to the whiteboard. So we'll start off with the first bit. This is part A. We have to show, that's the thing. In part A, we have to show that f dash of x is equal to negative tan of x. That's what we're required to do. So we're going to do it by just finding the derivative. So using the chain rule, f dash of x is equal to, we derive the inside, we find the derivative of the inside function. The derivative of cos is negative sine, so it's negative sine of x, and we multiply that by the derivative of the outside function, which is ln, with respect to the inside function. So it's 1 over, and the inside function is cos x, so it's 1 over cos x. You can probably see where we're headed now. Now, again, just because negative sine of x is all by itself, it doesn't mean that it's just floating. You can put it over 1 if you want to in your head. So it's negative. So multiply the tops together, we get negative sine of x. Multiply the bottoms together, we get cos of x. Now we know sine over cos is tan. The only thing is that there's a negative in front there, so it would be negative tan of x, which is what we were required to prove. So that's the end of that one. Okay, part B. It says hence show that the integral, or find the integral of tan of x ln of cosine of x with respect to x. So this is how we would go about it. It looks really complicated, but it's actually not. It's just reverse chain rule again, really. And if you look at the slide 5 there, we can see that there's ln, there's a function, and its derivative is tan of x, or negative tan of x, but it's there. There's that same function here, and the derivative is popped over here. So there's definitely something going on here that we can utilize, of course. And we can do it like this. Now, this is unusual. We haven't seen this before, and it requires us to think very carefully about what we're doing. Rather than letting u equal the inside function, I'm going to let u be the entire right-hand side of the product. So let u equal ln cosine of x. Okay, that whole right-hand side of the product there. And the reason why is because I'm going to build in what part A. So we know that du by dx is equal to negative tan of x. That's from part A. So that's where we've used it, i.e. du is equal to negative tan x dx. And we're ready to go. Now, I'll go one extra step just so that it's perfectly matching up, but you can actually do it from there by using your head. But I'm just going to say negative du is equal to tan x dx. And I did that so that this bit matches perfectly these two parts, negative du. And u is that bit there. Okay, so what we're left with is the integral. So the tan x dx is going to be replaced with negative du, and the ln cos x is going to be replaced with u. So we've got u negative du. So in other words, we're working out the integral of negative u du. Much simpler, huh? It does require you to think it through. Again, rather than being a slave to the formulas, what we're doing is we're going, well, what the name of the game is to replace all the x's with a simpler u expression and have it with respect to u. So by being able to piece these things together, you're able to get there. But it does require some careful consideration, which is what makes it a really good exam style question. Really trying to figure out whether you know what you're doing. Okay, so we've got the integral of negative u du. That's a pretty straightforward integration. Raise the power by 1. So it goes from u to the power of 1 to u to the power of 2. And we've got our half there, our reciprocal of the power. And we can't forget the negative that we had in there as well. So it's negative a half u squared plus c. And then we just substitute back in. So we've got equals negative a half ln cos of x. And the whole thing is squared. So it looks a bit ugly, but nevertheless, that's what it is. And again, that hence needs to be explicitly shown here. So from here to here, I've actually used part A, and I've labeled it as such, so it's definitely in there. And then we're able to solve it rather quickly. So generally, as a general piece of advice for the exam, when you do see the word hence, that's also a clue to you that there's something in the first part which will allow you to solve more easily the subsequent parts. So look out for that word hence and use them wisely. Okay, that'll do for this video. See you on the next video.